Okay, the app just crashed, so I'm gonna continue. So that was the left side, and on the right side, so we were comparing these areas. So you see that what the first area is. For the charge is on the surface. So it is really right here. This is the area, and this was the area before, but they are the same area. So you need to make sure of those things because they are not always going to be the same, and more mistakes are done if you're not checking. So since these two are the same, we're just going to cancel these out, and then we will get the electric field as, and cosine 0 is 1, simply sigma over epsilon naught. We did get something similar to that before, and it was not a quick integral like this one. It was in chapter 22 derivation. We had a 2 at the bottom. It was for non-conducting object, but this is a conducting sheet. We can also do that using Gauss law to find it, but right now we are just showing the electric field due to conducting sheet. And again, for, let's say, recall, E electric field, or E for non-conducting sheet, is sigma over 2 epsilon naught. There was 2 at the bottom. Okay, and we showed the derivation before. It was a really long derivation. It came from the disk. This came from the ring. If you remember those derivations, we did one of the first derivations. And Gauss law gives us that the same answer in just a couple lines. Okay, so next set of lesson objectives are: for a conductor with a cavity that contains a charged object, determine the charge on the cavity wall and on the external surface. As I mentioned before, now we are putting a charge, another charge in the cavity. And we'll explain how Gauss law is used to find the electric field magnitude near an isolated conducting surface with a uniform surface charge density. And for a uniformly charged conducting surface, apply the relationship between the charge density and the electric field magnitude E at points near the conductor and identify the direction of the field vectors. So let's see. First, we need to remember these. The electric field at and just outside the conductor's surface must be perpendicular to the surface. And if it were not, then it would have a component along the conductor's surface that would exert forces on the surface charges, causing them to move. We already said that even if it's a solid conducting object like a metal, solid metal, no cavities, let's say, if you dump some charge on it, all the charge will reach an equilibrium, electrostatic equilibrium, and by how are they going to do that? By spreading themselves evenly through the surface only. And what we're saying is that now the electric field must be perpendicular outside the surface because there's no electric field inside, so outside part is going to be perpendicular to the surface, because if it wasn't perpendicular, those charges which already reached the equilibrium, electrostatic equilibrium, they would move because of that horizontal component, or tangential, we should say, component on the surface. But they're not moving anymore. They're in equilibrium, right? So we don't want any tangential components of the electric field that would create force on the charges. And because such motion would violate our implicit assumption that we are dealing with electrostatic equilibrium, right? We are still working on electrostatic case, so we need to get that equilibrium, and we should not let anything mess that up, basically. And next we are going to do a sample problem. So here we have spherical metal shell and the electric field and enclosed charge. So I'm not showing the electric field lines here, but what happens if you put a charge negative Q? inside the cavity of a conductor shell. So we are saying that the shell is electrically neutral. What are the induced charges on its inner and outer surface? So we are putting a negative charge. You're not gonna put it right at the center. It's gonna be off-centered. Somewhere here maybe. Okay, that's the negative Q. And then what are the induced charges on its inner and outer surfaces of that shell? Okay. Before that, we had the cavity and we didn't have any charges in the inner surface, and everything was on the outer surface. Things changes when you put a charge inside the cavity, and we are now observing that. So we put a negative Q charge inside that shell. I mean, it's physically impossible because it's a closed shell, but theoretically, we are thinking about what would happen. And when you have negative charge inside, although the shell is neutral, it is going to attract positive charges nearby. Okay, and there will be more positives on the side of the shell, which is closer to that negative charge, and there will be less charges on the other side. Okay, and the total charge in the inner surface is going to be the same amount as the one inside the cavity, which is going to be positive Q, which will be in the inner surface. So the inner surface will have positive Q because we are placing a negative Q inside. So whatever you place inside inner surface of that shell is going to have the same amount but opposite sign because they are attracted to each other. And what about the outer surface of the shell? The shell was neutral. If we use positive Q in the inner surface, that really means that that negative charge that we put in the cavity is going to repel the electrons. And remember that we are dealing with a conducting shell, so the charges are free to move. Because of that negative Q in the cavity, pushing the electrons out, but they cannot go anywhere. They will stay in the shell. So they are just going to move to the outer shell. Okay, they're gonna because they're gonna move from the inner to outer shell, or inner to outer radius kind of, they are going to create holes in the inner surface, and we will call them positive charges, right? And the amount is the same as the charge we put in the cavity. So it's going to be as positive Q. For the outer surface then, if we are having, so whatever you have an inner and the outer, it should be the same as what you had initially. And this was neutral. So you're not really changing that because you're not touching it with the charge you put in the cavity. Okay, we are not really transferring the charges, we are just inducing, and this word is really important. So if the inner is negative Q, what would be the outer? You put the inner on the other side and switch the sign, right? It was positive. Now you can see that outer surface should be negative Q, so that when you add the inner and outer, you should still get neutral object. Okay, so a couple things here. Are those charges uniformly distributed? Let's think about inside and outside. So inside is like the inner surface again. You can already see that inner surface charges are not uniform because that negative Q was off-centered. If it was put in the center, then they would be uniform, but because it is put off-centered on the left side of the inner shell, inner surface, there will be more positive charges, and outside is going to be, the left side, the right side is going to have less amount of the charge. So it's non-uniform for inside. But outside, so that's going to be, this is a little different. Outside is going to be uniform. And the reason for that is, so that negative Q attracted positive Q, and I already showed the arrangement of that. But outer, so there's an equilibrium between those positives and the negative charge inside. Okay, in the same amount, the equilibrium is reached. Okay, and what will happen is now we got this because the electrons were pushed out, and they are going to be pushed out nicely and kind of like evenly distributed on the outer surface. So outside will have uniform charge distribution. Inside it won't, because that negative Q is off-centered, and that because of that you'll see that in one side there will be more charges than the other side inside that inner surface. And what is the field pattern inside and outside the shell? So you know that it starts from negative, it originates from positive and goes in the negative, so it's gonna go like that. I'm gonna try to draw as much as possible. So, and it's gonna be from positive to negative, like that. This is inner, and again, it is not uniform. And inside the conductor, there's nothing. Outside the conductor, because they're negative charges here, they're gonna be uniform, and it's gonna go towards the sphere. But they are uniform. They're really kind of straight lines and evenly spaced out. Okay. So inside the cavity, electric field lines are non-uniform, and it goes from the inner positive surface charges to the negative charge put in the cavity. That's the direction of the electric field. Outside, since we have negative net charge, when you look at the whole thing, the field lines are going to go in.